Mr. Heffernan here, and here's a short video on fluid flow rates. So your flow rate input is equal to your flow rate output. So flow rate is the rate at which fluid is moving. It is the volume per unit time. It may be measured in liters per second, cubic meters per hour, gallons per minute, or some other set of units. Three useful conversions to know are 1 liter is 1,000 milliliters. And since a milliliter is the exact same thing as a cubic centimeter, or sometimes called a cc, then a liter is also equal to 1,000 cubic centimeters. 1 cubic meter is 1,000 liters, and if that's water, it'll actually weigh have a mass of 1,000 kilograms, or 1 metric ton. And a gallon is 3.7854 liters, if you want to use a US gallon instead. So flow rate, just like the law of conservation of mass and energy, states the flow rate of a fluid into a system must be equal to the flow rate of a fluid out of the system. Or if you have a connection, whatever goes in to this connection right here must come out. So the volume input must be equal to the volume out. To do this, fluid must be fast in a tight pipe like this one, and it must be slow in a wide pipe like this one. So here, if you have a big cross-sectional area, the speed is going to be slow. Here, where you have a tight pipe, the speed is going to be fast. So once again, the units for typically for flow rate are liters per second, meters cubed per hour, gallons per minute, and the formulas are down below. So here is the symbol for flow rate, QV, and it's equal to the volume, big V, divided by time, T. Or it's equal to the velocity or speed, little v, times the cross-sectional area, A. So make sure your big V and your little v do look different, or you'll get confused. And then when you do go from two different sized pipes or hoses, your flow rate that goes in must be equal to the flow rate that comes out. So the speed times the area going in must be equal to the speed times the area coming out. So I'm just going to do 4 examples just to go through some of the math. So the first one, you've got a 5-gallon jug and it's filled in 1 minute. Find the flow rate. So first we're going to find the volume. We got 5 gallons times 3.7854 liters per gallon. So we're going to have just over 18.9 liters, 18.927. And of course, a minute is 60 seconds. So we're going to have our 18.927 liters divided by 60 seconds. So our flow rate is 0.315 liters per second, or about 315 milliliters per second. So basically about a soda can per second, approximately. So you can see the refill station where we get the big jugs filled in, or the garrafons. Okay, another example. This one's a more difficult one. There's lots of conversions, which makes it tricky. So here we are filling a swimming pool, and if the swimming pool is 15 feet across and 3.5 feet high when it's full, and we're filling it with a 5/8 inch garden hose, and it takes 5 hours to fill it, then how fast is the water spraying out of the hose? So we're going to use the flow rate formula for this. So flow rate's volume over time times speed times cross-sectional area. So the volume of a cylinder, like a pool, is pi r squared h, and the cross-sectional area of the hose is pi r squared. So here we're going to get half the diameter of the pool, so half of 15 feet is 7.5 feet. And then we got the height, which is 3.5 feet. So altogether, we're going to get pi times 7.5 feet squared times 3.5 feet over 5 hours. So the flow rate is 123.7 cubic feet per hour. But on the other side, we have the speed times the pi times half the diameter of the hose is 2.5/8 of an inch. But if we're using cubic feet over here, then we probably want to use feet over here as well. So we're going to divide by 12 to get the feet. So 2.5, which is half of the 5, 8 for the eighths, and then divide by 12 to turn into feet, and we're going to square that. When we rearrange the equation to get speed, we get 39.375 cubic feet per hour, divided by 2.5, divided by 8, divided by 12 in brackets, feet, all squared. And then we're going to change the 1 hour into 3,600 seconds. And so we're going to get a total speed or velocity of 16.128 feet per second, or sometimes it's labeled FPS. So the hose is going to spray the water at around 16 feet per second, which is around 4.9 meters per second, half the speed of an Olympic sprinter. Okay, so that was a tough example. Now here's a little slightly easier one. So here we got a water main, like a giant pipe underground, with the water traveling through really slowly at 5 centimeters per second, so 0.05 meters per second. And the radius of this pipe, or this water main, is 1 meter, which means it has a diameter of 2 meters. And then it's going to shrink down into this pipe here, where the radius is only 4 centimeters, or the diameter is 8 centimeters altogether. So we just want to find out what's the speed right here in the small pipe. So the speed input is equal to, so the flow rate input is equal to the flow rate output. So speed times area equals speed times area. Both of them are circles, pi r squareds. And so we're going to fill it in. So the first one is 0.05 meters per second. We've got a pi out right here, 1 meter in radius squared. And on the other side we have speed 2, pi, and then 0.04 meters squared. The pi's cancel out since there's a pi on both sides, and when you do the calculation you get 31.25 meters per second, which is really fast, 113 kilometers per hour approximately. Okay, last question, example 4. Water sprays from a hose partially covered by a finger at 15 meters per second, and the area that's left open right here is only 0.015625 square inches. So if the hose has a diameter of 5/8 of an inch, which is your typical US garden hose, then what is the speed inside the hose, right around here? So to find out, the speed input is equal to the speed output. So we have speed times area equals speed times area again. Both are circles. Well, sorry, the side that's right over here is a circle, pi r squared. And we already know the area on the other side. So we're going to get speed times pi times 5/8 of a hose divided by 2 for the radius, inches squared, equals 15 meters per second times the cross-sectional area left by the finger, which is 0.015625 square inches. And when we calculate it, we get a speed of 5.24 meters per second. And oops, a little typo, forgot to erase this down below. Anyway, so 5.24 meters per second, that's about half the speed of an Olympic sprinter. So someone running really fast would outrun that hose. So flow rate is how quickly fluid is moving, and is the rate of volume per unit time. So your flow rate is calculated by the volume divided by time, or the speed times the cross-sectional area. And it should be useful in calculating things like fire hose speed. And conservation of flow is just like the conservation of mass and energy. The flow rate passing into a connection must be equal to the flow rate coming out of a connection. I hope this video has been useful.